Vacuum birefringence phenomenon in the endless black sea of space, where even time seems to hold its breath. We once believed there was silence, pure, inert emptiness. The vacuum was thought to be nothing at all. A backdrop. A void, but the more we listened, the more we stared into the dark, the more we realized, the vacuum is alive. This is where the phenomenon of vacuum birefringence emerges, a subtle distortion of light itself, predicted nearly a century ago and only recently caught in the act. It begins with a simple question: what happens to light in a perfect vacuum, surrounded by an unimaginably strong magnetic field? To the naked eye, light always travels in a straight line, unbothered, untouchable. But in the bizarre realm of quantum electrodynamics, that's not the whole truth. There, even light can stutter, splitting into different polarizations, like it's entering a crystal. Except here, the crystal isn't real. It's just space. Or at least, what we used to think was just space. In the quantum world, a vacuum is far from empty. It's a wild and foaming arena, filled with virtual particles that flash in and out of existence in fractions of a second, borrowing energy from nothing and then vanishing before they can be seen. These are not fairy tales. These are foundational truths of our universe, and they happen all around us, all the time. When a strong magnetic field enters this quantum vacuum, something like the field surrounding a neutron star, it warps these invisible fluctuations. It twists the rules. And the photons of light passing through this twisted space behave differently depending on their orientation. Light becomes sensitive to the unseen. It splits. It bends. It reacts. This phenomenon, vacuum birefringence, was theorized by Werner Heisenberg and Hans Euler in 1936, long before we had the tools to observe it. They didn't know when it would be confirmed, only that it was inevitable. Fast forward to 2016. Astronomers turned their telescopes toward a neutron star called RxJ 1856.5-3754, a dead sun crushed into the size of a city, spinning rapidly and wrapped in magnetic forces strong enough to tear atomic structures apart. They measured its visible light, expecting a normal signal. But what they saw instead was unusually high polarization, light that seemed too orderly, too affected, as if something invisible had reached into the beam and altered it. This wasn't the behavior of light in a vacuum. It was the behavior of light in a bent vacuum, one affected by magnetism, by quantum instability, by something. The only explanation? Vacuum birefringence. In that moment, an idea passed from theory to reality. We had caught the void in the act, but here's where it becomes more than physics. If the vacuum, the nothing, between all things, is reactive, structured, interactive, then maybe it isn't truly nothing at all. Maybe it's a hidden fabric, a medium for unknown forces, or a veil covering deeper dimensions. Maybe the real architecture of our universe isn't built from matter, but from the rules of absence, a place where energy and information dance invisibly in the gaps we overlook. Vacuum birefringence isn't just a weird scientific effect. It's a whisper from the other side of reality, a quiet signal that space itself may not be passive. That the nothingness between stars holds a kind of memory. That the universe, even in its silence, is always speaking, and perhaps, if we listen closely enough, we might begin to understand the language of the void. The Janus point theory: when we think of time, we imagine a one-way street. The past sits behind us, distant, unreachable. The future waits ahead, uncertain and untouched. But what if this entire perspective is wrong? What if time is not a river flowing forward, but a tide that ebbs in both directions from a single origin point? That's the proposition at the heart of the Janus point theory, a deeply provocative idea put forth by physicist Julian Barbour, who has spent decades reimagining the fabric of time. In a world where the arrow of time is considered one of the few untouchable truths, this theory doesn't just bend it, it breaks it in half. To understand the Janus point, we have to first confront the enigma of entropy, the gradual decline of order into chaos. In classical thermodynamics, entropy increases over time, and it's this increase that gives time its forward momentum. It's why eggs don't unscramble, why smoke never returns to the fire, why childhood becomes memory. But here's the paradox: the core laws of physics, Newtonian, quantum, even relativistic, are time-symmetric. They don't care whether you run the clock forward or backward. They work the same. The fundamental equations are blind to the direction of time. So where does the arrow come from? Barber suggests it's not embedded in the laws, it's emergent. And the Janus point is the key. Imagine the entire universe compressed into a single state of lowest possible entropy, not dense like the Big Bang necessarily, but ordered to the extreme. From this minimal complexity, the universe begins to evolve in two symmetrical directions, each with its own increase in entropy. One of those directions is what we experience as the future. But the other? It's not our past, it's a mirror reality, where time appears to move the opposite way, not backwards, but outward, just like ours. This moment of symmetry, the Janus point, is not a traditional origin. It's a kind of cosmic fulcrum, a zero point from which two temporal branches emerge. The universe, in this view, doesn't have a beginning and end. It has a center, and from that center, two universes unfurl like wings of a butterfly. We could imagine beings in that mirror universe. They would watch stars form and galaxies expand just as we do. To them, their time feels just as forward as ours. From their vantage, we are the ones living in reverse. But here's the kicker: according to Barber's work, time itself might not be fundamental at all. In his framework of shape dynamics, time is an illusion. It doesn't exist as an external force. Instead, what exists is change, the shifting of relationships, the unfolding of shapes and structures. The Janus point isn't a ticking moment, but a geometric configuration of maximum order. It's not when time started, but when complexity was at its lowest, and from there, the dance began. The more the universe evolves from that point, the more entropy increases, the more structure appears, and the more consciousness emerges. So while it may feel like we're heading toward disorder, what we're really doing is moving away from symmetry, into greater diversity, complexity, and possibility. In a sense, we are not watching the universe decay. We're watching it blossom in both directions. This reframing changes everything. If true, the Janus point theory doesn't just solve the mystery of the arrow of time, it reframes existence as a twin unfolding of reality, where before and after are relative, where the universe is not a dying clock but a living mirror, and in the silence beyond stars, beyond the edge of what we know, another universe could be blooming. Not a replica, not a shadow, but a twin. Born from the same seed, unfolding its own story, with its own time, and perhaps, somewhere at the heart of both stories, lies that quiet, sacred center, the Janus point, where the past and future touch, and time itself remembers being still. Time crystals: imagine a clock that ticks forever without winding. A pendulum that swings back and forth endlessly, never slowing, never stopping, not because it's powered by gears or electricity, but because it exists in a completely different state of matter. That's the reality, not metaphor, behind time crystals, one of the strangest phenomena ever discovered in modern physics. Let's break it down. In our everyday understanding of crystals, like diamonds or snowflakes, they're defined by symmetry in space. Their atomic structures repeat in fixed patterns, stretching out in three-dimensional lattices. They're stable, ordered, predictable. But in 2012, Nobel laureate Frank Wilczek proposed something that flipped that idea on its head. What if a structure could repeat not in space, but in time? That's the core of a time crystal. Instead of remaining frozen in one state or drifting toward thermal equilibrium, as all systems eventually do, a time crystal pulses, switching between configurations in a predictable, repeating rhythm, without expending energy. It doesn't just exist in time, it cycles through it. This is known as discrete time translation symmetry breaking, a mouthful, but it means that the system's state changes with regular intervals, even though it's being driven by a consistent, steady input. Think of it like tapping a bell at regular intervals. but instead of responding to every tap, the bell only rings on every second or third tap. It finds its own rhythm, out of sync with the driver. That rhythm is baked into its existence. To create this in the lab, scientists used finely tuned quantum systems, such as chains of qubits, or trapped ions cooled to near absolute zero. In 2016, two separate teams, at Google and the University of Maryland, demonstrated this effect independently. They pulsed the systems at regular intervals, and the quantum bits flipped in a repeating pattern, not driven by the pulses themselves, but by a deeper internal dynamic. The system chose its own tempo. Here's where it gets weird. In classical physics, you can't have motion without energy. But in the quantum world, things don't play by those rules. A time crystal is in a ground state, its lowest energy configuration, and yet it changes over time. That's like a pendulum swinging without gravity or friction. It challenges our fundamental understanding of thermodynamics, entropy, and time itself, but don't confuse time crystals with perpetual motion machines. They don't break conservation laws. They're not free energy. Instead, they live in a bizarre loophole of non-equilibrium quantum mechanics. They remain in motion, not because they're being powered, but because they've found a loophole in how systems evolve. This matters a lot. Time crystals may hold the key to next-generation quantum computing, where stable, coherent qubit states are essential. The fact that they can maintain oscillations indefinitely, without decohering or losing energy, means they could serve as perfect timekeepers or quantum memory platforms, potentially unlocking massive leaps in technology. But the implications run even deeper. The discovery of time crystals challenges our assumptions about what time even is. Is time a one-way arrow? Or is it a medium with hidden structure? Can matter have a temporal architecture, just as it has a spatial one, and what if such structures occur naturally? Some physicists speculate that the early universe, when energy densities were high and conditions exotic, could have birthed naturally occurring time crystals. Could remnants of those structures still echo through cosmic background radiation? Could the quantum foam of space itself ripple with hidden temporal order? It opens the door to a new way of thinking about reality, where time isn't just a backdrop for events, but a dynamic arena, shaped and structured like space. Time crystals are a whisper from that deeper framework, suggesting that there's still a hidden geometry to time, waiting to be decoded. It's as if the universe is ticking, not because of external motion, but because of something inherent, something woven into the code that we use to think of time as a straight line. Time crystals suggest it might also be a rhythm. A loop. A beat. A hidden pulse in the heart of everything, and we've only just started listening. Dark flow. Imagine you're standing on the shore, watching the tide roll in. Every wave has a rhythm, a direction, a pattern. But suddenly, one current seems to move independently, pulling in a direction no one expected, as if tugged by something beyond the ocean itself. That's the cosmic equivalent of dark flow, a mysterious motion of galaxy clusters that defies the known boundaries of our universe. Here's what makes it mind-bending. In the standard model of cosmology, the universe is expanding uniformly. Thanks to the Big Bang and the inflationary epoch, galaxies are receding from each other, with local motions, like the Milky Way drifting toward Andromeda, layered on top. But on the largest scales, hundreds of millions of light-years across, things should average out. There should be no preferred direction, but that's not what we found. In 2008, a team of astrophysicists led by Alexander Kashlinsky analyzed data from the Wilkinson Microwave Anisotropy Probe, WMAP. They were studying the kinetic Sunyaev-Zeldovich effect, where cosmic microwave background, CMB, photons scatter off moving galaxy clusters. What they discovered sent shockwaves through the astrophysics community. A large number of galaxy clusters, spread across vast regions of the observable universe, appeared to be drifting in the same direction. And not just slightly. They were moving at speeds of up to 600 to 1,000 kilometers per second, all pointing toward a region of sky near the constellation Centaurus. This wasn't normal galactic movement. It wasn't caused by local gravitational effects. It seemed to be a coherent flow, as if something massive, something outside the observable universe, was pulling on these galaxies, hence the name, dark flow. Now here's the real kicker: scientists don't know what's causing it. The standard model of cosmology can't explain it. The observed universe, with all its matter and dark matter, doesn't contain enough mass in that direction to account for such a pull. So what's out there? One possibility is that our universe is just a small part of a much larger multiverse, and that this flow is the gravitational fingerprint of another universe, a cosmic neighbor, beyond the limits of what we can see, but close enough to exert an influence. Others speculate that primordial structures, formed during the inflationary era, before the CMB even cooled, could be responsible. Remnants from a pre-Big Bang state that shaped the flow of matter long before light could travel. And then there's the unsettling idea that dark flow is evidence that our universe isn't isotropic, that the cosmos does have a direction, a structure, or even a center. If true, that would upend one of the core assumptions of modern cosmology, the cosmological principle, which holds that the universe is the same in all directions, on large scales. Of course, some scientists remain skeptical. Later data from Planck didn't confirm the original findings, though interpretations vary. The evidence is debated, but not debunked. Dark flow lingers, an unresolved anomaly on the edge of everything we know, but here's the thought that keeps physicists up at night: if dark flow is real, then something beyond the cosmic horizon, beyond time and space as we know it, is pulling on our universe. Not metaphorically. Not spiritually. Literally, something we cannot see, something we cannot reach, something massive enough to drag galaxy clusters across the cosmos. It raises a chilling question: what lies beyond the edge of our universe? Quantum Darwinism. We've all heard that observation creates reality in quantum mechanics. It's a seductive phrase, but also deeply misunderstood. Quantum Darwinism takes that confusion and flips the script. You don't create reality by observing it. Reality creates itself by deciding what's worth being observed. Let's start with the core mystery of quantum mechanics: superposition. A quantum system, like an electron, exists in multiple states at once until it's measured. It's here and there, spinning up and down. But when you look at it, bam, it chooses one. The classic Copenhagen interpretation says your act of measurement collapses the wave function into one reality, but that always left a nasty philosophical itch. Are we really saying reality is undefined until someone with a brain shows up to look at it? Enter quantum Darwinism, a theory that removes the need for conscious observers. Instead, it says, the environment acts as a measuring device. Not a person. Not a scientist. Just everything around a quantum object: light particles, air molecules, cosmic background radiation. These things constantly interact with quantum systems, watching them long before we do. But what does that watching mean? Here's where the Darwinism kicks in. When a quantum system interacts with its environment, it starts leaving copies of information about itself: what state it's in, how it's behaving. These bits of data get imprinted across the environment, again and again, redundantly, like a file backed up on thousands of cloud servers. That's decoherence, the mechanism that kills off superposition. But here's the kicker: not all quantum states can survive this process. Just like in biological evolution, only some mutations thrive. These are the pointer states, stable configurations that can be copied, transmitted, and still make sense. The unstable ones? Too fragile. They disappear, lost in the noise. They never make it to your senses. So your experience of a chair, a rock, or the moon isn't the only possible version. It's just the version that survived replication, the one that the universe voted into existence by making billions of environmental copies of it. That's why we all see the same moon. Not because it exists in some objective sense, but because its pointer state is echoed in trillions of photons bouncing off its surface, interacting with the atmosphere, your retina, your camera. Those photons carry one consistent message, selected by nature through quantum natural selection. Now think about what this means. Objective reality is an illusion of agreement. Truth is what the universe can copy best. What you don't observe isn't necessarily gone, it's just not reproducible enough to matter. And the creepiest implication, if a quantum state can't be copied, it's effectively erased from reality. Permanently. No record. No memory. No observer will ever know it existed. That's not just deep, that's existential. In a way, quantum Darwinism suggests the universe curates its own history, by allowing only the most stable, redundant information to be perceived. Your brain, a receiver, not a projector, tunes into this cosmic playlist of survivable data, playing the greatest hits of matter and energy, over and over again. It also means that consciousness might not be as magical as we once thought. We're not the architects of reality, we're just another system interpreting the environment's broadcast. A late arrival to a show that's been running since the Big Bang, so when you look around and feel like the world is stable and solid and agreed upon by everyone, that's not the universe being simple, that's the universe being efficient. It's not giving you the truth. It's giving you the most evolved version of the truth that can survive observation. Geons, reality's most elusive ghosts. At the edge of theoretical physics, where our understanding of space and time begins to warp, there exists a concept that is as radical as it is elegant: geons. These are not particles, not waves, and not objects in any conventional sense. They are spacetime constructs, born from energy itself, and they could fundamentally challenge what we think matter actually is. Proposed in the 1950s by physicist John Archibald Wheeler, geons, short for gravitational electromagnetic entities, are essentially self-contained energy loops, where light or other fields are trapped in spacetime by their own gravitational influence. They have no solid center, no atomic core, they are made entirely of curved spacetime and circulating energy. They're not objects within space, they are space, twisted into knots. To truly grasp geons, you need to embrace the idea that energy can shape spacetime, and spacetime can trap energy. In a perfect balance, the two can create a self-sustaining system. Imagine a photon caught in a gravitational loop, forever spiraling through a closed curve of warped geometry, forming a stable, localized pattern of energy that mimics a particle. Think of it as a smokeless fire, or a whirlpool made of nothing but the water's own motion. A geon is a ripple that doesn't fade, and here's where it gets really mind-bending. Wheeler realized that if such structures could exist, they might not just resemble particles, they could be the particles. An electron, a quark, a muon, maybe these aren't tiny billiard balls. Maybe they're just self-reinforcing waves of field energy, locked into place by spacetime curvature, without any physical stuff inside at all, just geometry, just spacetime playing tricks on itself. Geons also speak to one of the deepest mysteries in physics. Why do particles have mass, charge, or spin? If a geon could exhibit all of these properties, purely from the way spacetime and fields are arranged, then perhaps we don't need to add these qualities to particles. Perhaps they're just emergent effects of geometry. Now, let's address the elephant in the room. Why haven't we seen one? That's the catch. Geons, in their original form, are thought to be unstable. Over time, they'd radiate away their energy, unwinding like a clock with no gears. But there's still hope. Theorists suggest that under certain conditions, like in the intense gravitational field of a black hole, geon-like structures might persist. In fact, the very idea of quantum gravity might breathe new life into geons. If spacetime at the smallest scales behaves more like a network or foam, then geons could emerge as knotted or braided energy patterns, living in this quantum substrate. This ties in with modern theories like loop quantum gravity, twistor theory, and causal set theory, all of which hint that reality might be made of connections, not objects. And there's a poetic twist here. Ancient philosophies, especially in the East, have long spoken about the illusion of form, the idea that solidity is an illusion, that everything is vibration, pattern, impermanence. Wheeler was ahead of his time. He saw the universe not as made of particles, but of information and geometry. He even famously said, "It from bit," suggesting that everything, matter, energy, even spacetime, might emerge from informational processes. Geons are a glimpse into that possible truth. They're the mathematical ghosts of a universe made not of substance, but of structure. In a strange way, they are existence without essence, a ripple that holds its own shape, even if there's nothing truly there. So next time you touch your hand to the table or look at your reflection, remember this: beneath the atoms, beyond the particles, there may be no matter at all, just patterns. Just loops. Just geometry folding in on itself, long enough to be called real. The cosmic censorship hypothesis: imagine a universe where the very fabric of reality breaks down, where our physical laws are no longer able to explain what's happening. Where time and space lose their meaning, and the core of existence becomes an unintelligible void. This is the terrifying possibility suggested by naked singularities, and it's exactly what the cosmic censorship hypothesis is trying to prevent. Let's start from the beginning. What are singularities? Singularities are points in spacetime where gravity becomes infinite, and the normal rules of physics simply cease to apply. These points are believed to exist at the center of black holes. Picture it: an infinitely dense point where space and time are crushed into an unrecognizable form. When a star collapses under its own mass, the gravitational pull becomes so intense that the core can become a singularity. But here's the problem: singularities are dangerous to our understanding of the universe. Why? Because singularities are places where our laws of physics break down. They're not just points where things get weird, they're areas where we cannot even apply the mathematical equations we've so carefully developed over centuries. There's a no man's land in the laws of physics where spacetime itself implodes into chaos. If singularities existed in the open universe, they would create a total breakdown in causality, the very notion that events follow a clear cause and effect relationship. Imagine if the future could change at random. Predictability would collapse, and science would be meaningless, and that's where cosmic censorship comes in. What is cosmic censorship? In the 1960s, the renowned physicist Roger Penrose proposed the cosmic censorship hypothesis. The basic idea is simple: the universe will never let naked singularities exist in open space. In essence, cosmic censorship is the law that the universe hides singularities from us. Whenever a singularity tries to form, it will always be wrapped up in an event horizon, the boundary around a black hole that no light can escape from. The singularity is censored and shielded from our perception, and we're left with just a black hole, a cosmic object that obeys the laws of physics. Why is this important? Because if naked singularities did exist, it would mean the breakdown of reality as we know it. It would create a scenario where physics no longer made sense, where our entire understanding of space, time, and causality could unravel. In a sense, cosmic censorship is what keeps the universe functional. It's the invisible safety net that ensures the fabric of reality doesn't fall apart. It's the reason we can confidently study the cosmos without worrying that the rules will suddenly collapse under our feet. The disturbing truth: does cosmic censorship actually hold? While the cosmic censorship hypothesis is an elegant solution, we have no definitive proof that it's true. It's more of a conjecture, a strong idea with no evidence to fully support it. Penrose's theory works in principle, but there are a few challenges. For example, some theorists believe that naked singularities might not be as rare as we think. Under extreme conditions, like in certain types of rotating black holes or in higher dimensional space, there could be scenarios where singularities emerge without an event horizon to hide them. These theoretical models challenge the idea that cosmic censorship works every time. One example is the naked singularity created in a rotating black hole. If a black hole rotates at high enough speeds, it's possible that its event horizon might not form properly, exposing the singularity to the outside world. While we've never seen a naked singularity, simulations in certain conditions have suggested they could theoretically appear. But so far, we haven't observed one in nature. Why is cosmic censorship so important? The answer is simple: without the veil that cosmic censorship provides, we would be staring into a reality without order, without causality, without the predictability that makes our universe comprehensible. Our ability to predict the future would vanish. The universe would no longer make sense. In essence, the cosmic censorship hypothesis provides the stability we take for granted in science. It maintains the laws of physics as a foundation for understanding, ensuring that even in the most extreme conditions, like black holes and singularities, our physical theories continue to work, at least in the regions we can observe. Without it, the laws of physics would not only be incomplete, they would be utterly meaningless. But here's the catch: we still don't know if it's true. We may never know for sure. The only way to test the theory is to observe the conditions in which a naked singularity might form, but if cosmic censorship is working, it's likely that we'll never get the chance to observe one. It's a self-perpetuating rule that in a sense, cosmic censorship is like the universe's own form of self-preservation. It's the ultimate safeguard against the destruction of order, making sure that the mind-bending, unpredictable chaos of naked singularities stays hidden from us, and perhaps, from ourselves. A final thought: the ultimate mystery, the idea that our universe might be protecting us from a total collapse in causality, is a deeply philosophical question, one that asks us whether reality is inherently ordered, or whether it hides its deepest secrets to keep us from losing ourselves in them. If cosmic censorship does exist, it might be the universe's way of keeping us safe from the unknowable, and so, we return to the haunting question: what if we could see through the veil? What if we could peek at the naked singularities lurking beyond the boundaries of reality? Would we truly understand them, or would we go mad trying? With that, the mystery of cosmic censorship will continue to echo through the halls of physics, providing a tantalizing, almost metaphysical boundary between what is known and what is forever hidden. ER equals EPR conjecture. The ER equals EPR conjecture, proposed by physicists Juan Meldacena and Leonard Susskind in 2013, has captured the imagination of many in the field of theoretical physics. It offers an intriguing and somewhat counterintuitive idea that combines two seemingly distinct areas of physics: the concept of wormholes from general relativity and quantum entanglement from quantum mechanics. At the heart of the conjecture are two key elements: the Einstein-Rosen (ER) bridge and the Einstein-Podolsky-Rosen (EPR) paradox. The EPR paradox, introduced in 1935 by Albert Einstein, Boris Podolsky, and Nathan Rosen, explores the strange phenomenon of quantum entanglement. When two particles become entangled, the state of one particle is instantaneously correlated with the state of the other, regardless of the distance between them. This connection seems to defy the limitations of classical physics and is one of the foundational mysteries of quantum mechanics. It suggests that particles can share information faster than the speed of light, which contradicts Einstein's theory of relativity. On the other hand, the ER bridge refers to the theoretical structure in general relativity that describes what is known as a wormhole. A wormhole is essentially a shortcut through spacetime, a tunnel-like structure that connects two distant points in the universe. The concept of wormholes has been largely theoretical, with no direct experimental evidence supporting their existence, but they offer fascinating possibilities for understanding the nature of spacetime and how the fabric of the universe can be bent or manipulated. In essence, the ER bridge is a way of imagining how space itself could be distorted to create an efficient connection between far-off regions of space. The ER equals EPR conjecture proposes that these two ideas, quantum entanglement and wormholes, are not separate phenomena, but rather two sides of the same coin. According to the conjecture, entangled particles, as described in the EPR paradox, are connected through an Einstein-Rosen bridge, essentially suggesting that quantum entanglement is physically realized as a wormhole. This conjecture attempts to unite two seemingly incompatible frameworks of physics, quantum mechanics and general relativity, by showing that they are, in fact, deeply intertwined. One of the most intriguing implications of ER equals EPR is its potential to resolve the black hole information paradox. The paradox arises from the question of how information about matter that falls into a black hole can ever be recovered. If the information is lost beyond the event horizon of the black hole, it creates a contradiction with the principles of quantum mechanics, which state that information cannot be destroyed. The ER equals EPR conjecture suggests that wormholes, or ER bridges, might provide a way to retrieve this information, thus offering a potential resolution to this long-standing puzzle in theoretical physics. The ER equals EPR idea also has profound implications for the nature of spacetime itself. It suggests that space is not a static, passive backdrop to the universe but is instead a dynamic entity, deeply influenced by quantum phenomena. If entangled particles are connected through wormholes, this challenges our conventional understanding of space as a rigid structure. It hints at the possibility that the boundaries between different realms of physics, quantum mechanics, general relativity, and spacetime, are far more fluid and interconnected than we had previously imagined. This hypothesis is still largely theoretical, but it has sparked significant interest in the physics community. If proven to be correct, the ER equals EPR conjecture could lead to a breakthrough in the search for a unified theory of quantum gravity, a theory that would reconcile the differences between quantum mechanics and general relativity and offer a more complete understanding of the universe at its most fundamental level. Moreover, ER equals EPR challenges our very perception of reality itself. If wormholes and entanglement are linked in the way that the conjecture suggests, it could mean that the fabric of space is not just something that holds matter but is fundamentally shaped by quantum interactions. The implications of this idea are vast, suggesting that our universe could be far more interconnected, complex, and strange than we have ever imagined. From faster-than-light travel to the potential resolution of the mysteries of black holes, the ER equals EPR conjecture holds the tantalizing promise of reshaping our understanding of the cosmos. In conclusion, while the ER equals EPR conjecture remains speculative, it represents a bold step toward bridging the gap between two of the most powerful theories in physics. It provides a glimpse into a universe that is far more mysterious and intricate than we could have ever imagined, offering a vision of reality where the boundaries between quantum mechanics, relativity, and spacetime blur into one seamless whole. Whether or not this conjecture ultimately proves to be true, it has already contributed to a deeper understanding of the fundamental workings of our universe. Noncommutative geometry. Noncommutative geometry is a sophisticated and abstract branch of mathematics that extends classical geometry into the quantum realm. In traditional, classical geometry, the coordinates of space commute with each other, meaning that the order in which you multiply them doesn't affect the result. This is a simple and intuitive concept. However, quantum mechanics, which governs the behavior of particles at very small scales, shows that this assumption doesn't always hold true. In fact, in the quantum world, certain quantities like position and momentum don't commute, which means the order in which they are applied does have an effect, a principle that is encapsulated in the Heisenberg uncertainty principle. Noncommutative geometry provides a mathematical framework to understand this breakdown of classical assumptions. In the quantum world, space itself behaves differently. Noncommutative geometry is used to describe spaces where traditional rules don't apply and coordinates can no longer be considered independent from one another. The interactions between these coordinates become dependent on their order, leading to new ways to model reality at the smallest scales. At very tiny scales, near the Planck scale, our classical understanding of space and time collapses. Noncommutative geometry emerges as a powerful tool to explore the behavior of spacetime under these extreme conditions, where quantum effects dominate. One of the most significant applications of this concept is in string theory, where it is used to model higher-dimensional spaces beyond the familiar three dimensions. These additional dimensions, while not directly observable, are vital in string theory's quest to unify the fundamental forces of nature. In the context of quantum field theory, noncommutative geometry plays an essential role in understanding the structure of spacetime itself. It provides new mathematical tools to describe objects like black holes, and might even offer insights into the very early universe, right after the Big Bang. One particularly exciting possibility is that noncommutative geometry could resolve paradoxes such as the information loss problem in black holes, offering a potential breakthrough in one of the most puzzling issues in modern physics. Beyond its use in high-energy physics, noncommutative geometry also holds promise in condensed matter physics. In this area, it has been used to describe topological phases of matter, including materials known as topological insulators. These materials have remarkable quantum properties, such as conducting electricity on their surfaces while remaining insulating inside. By applying noncommutative geometry, scientists are better able to understand these unusual and counterintuitive quantum systems, opening the door to potentially revolutionary new technologies. Another important feature of noncommutative geometry is its ability to bridge different areas of physics. It connects quantum mechanics, general relativity, and string theory, offering a unified framework that might one day help to reconcile these different forces into a single, cohesive theory of everything. This ability to unify disparate areas of physics makes noncommutative geometry an essential part of modern theoretical physics, offering new insights into the fabric of reality itself. As we push further into the exploration of quantum systems, noncommutative geometry will undoubtedly play a central role in advancing our understanding of the universe at its most fundamental level. The idea that space itself may not be as simple as it appears, and that the fundamental components of reality could be more complex and intertwined than previously thought, makes noncommutative geometry one of the most exciting and promising fields in the ongoing search for the ultimate laws of physics. It offers new ways to think about the universe and opens up previously unimaginable possibilities for how the cosmos operates on its deepest, most mysterious levels. Unparticle physics. Unparticle physics is an intriguing and speculative branch of theoretical physics that suggests the existence of a new class of unparticles, hypothetical, non-integral particles that behave in ways entirely different from the familiar particles of the Standard Model. Unlike conventional particles, which have defined properties such as mass, charge, and spin, unparticles are thought to exist in a state where these characteristics do not apply in the conventional sense. Instead of being characterized by a specific mass or energy, unparticles are theorized to have a continuous spectrum of possible properties, making them radically different from anything we currently observe in particle physics. The concept of unparticles was introduced by physicist Howard Georgi in 2007 as an extension of the Standard Model, which describes the known fundamental forces and particles of the universe. In his groundbreaking theory, Georgi suggested that unparticles could arise from a scale-invariant quantum field, a field that doesn't rely on fixed, quantized units like the fields associated with particles. This scale invariance means that unparticles can exist in a form that isn't tied to the discrete energy levels that ordinary particles possess. Unparticles, by definition, would have no rest mass or fixed energy levels. They would not fit into the conventional particle classification, and as such, they challenge our usual understanding of the physical world. They could also lead to new insights in various areas of physics, including high-energy physics, cosmology, and even quantum gravity, potentially offering a new way to look at forces and interactions in the universe. One of the most remarkable properties of unparticles is their possible ability to interact with known particles in novel ways. For instance, unparticles could exhibit universal properties that allow them to influence other particles or fields in ways that are not captured by the Standard Model. The interactions of unparticles could potentially explain certain phenomena that remain mysterious or unexplained, such as dark matter, which is thought to make up a significant portion of the mass in the universe but does not interact with light or conventional matter in any detectable way. By extending the range of interactions in new directions, unparticles could open doors to explaining such elusive concepts. Furthermore, unparticles could provide insights into the behavior of matter under extreme conditions, such as inside black holes, or in the very early universe just after the Big Bang. They might even play a role in understanding the deep connections between gravity and quantum mechanics, shedding light on how these two fundamental forces of nature might be reconciled in a theory of quantum gravity. Experimental verification of unparticles remains elusive. However, unparticle physics is not without its testable predictions. Scientists have proposed that unparticles could be detected through their interactions with particles in particle accelerators like the Large Hadron Collider, LHC. These interactions could potentially leave behind distinctive signatures that differ from those produced by conventional particles, making unparticles detectable under the right experimental conditions. Such experiments could provide evidence for the existence of unparticles and open up new avenues of research in theoretical and experimental physics. Unparticle physics, while still highly speculative, represents an exciting frontier in the quest to expand our understanding of the universe. The potential for discovering entirely new types of matter and interactions makes unparticles a fascinating and challenging area of study. If proven to exist, unparticles could drastically change our understanding of the fundamental nature of reality, bridging gaps between quantum mechanics, general relativity, and the Standard Model in ways we have yet to imagine. Ultimately, unparticle physics underscores the constant evolution of our theories about the universe. Just as the discovery of quarks and neutrinos once revolutionized our understanding of matter, the possibility of unparticles challenges the very foundations of particle physics, hinting at new realms of phenomena and forces waiting to be discovered. Information paradox firewall hypothesis. The information paradox firewall hypothesis is one of the most controversial and speculative ideas in modern theoretical physics, particularly in the field of black hole physics. It seeks to resolve the paradox that arises from the interaction between quantum mechanics and general relativity, specifically regarding the behavior of information inside a black hole. The paradox has significant implications for our understanding of the fundamental nature of reality and the mechanics governing the universe. At the heart of the information paradox is the question: what happens to the information contained within matter that falls into a black hole? According to classical general relativity, when something crosses the event horizon of a black hole, it is lost to the outside universe, unable to escape due to the extreme gravitational forces. However, quantum mechanics suggests that information cannot be destroyed, even in such extreme conditions. This leads to what is known as the black hole information paradox, a conflict between the two theories. To resolve this paradox, physicists have proposed the idea of a firewall at the event horizon of a black hole, which serves as a dramatic solution to the issue. The firewall hypothesis suggests that instead of the event horizon being a smooth boundary through which matter can pass without experiencing any significant effects, it may instead be surrounded by an intense region of high-energy radiation, a firewall. This firewall would effectively destroy anything that crosses the event horizon, incinerating it and preventing information from ever being lost. The idea of a firewall is controversial because it contradicts a fundamental principle of general relativity called the no-drama principle, which states that objects falling into a black hole should not feel any immediate effects at the event horizon. They would pass through without noticing anything unusual. The firewall hypothesis challenges this principle by suggesting that there would, in fact, be a violent and dramatic end to any object or information that crosses the event horizon. This leads to a deeper question: if the firewall hypothesis is true, it would imply that information is permanently destroyed inside the black hole, which contradicts quantum mechanics, where the preservation of information is fundamental. The information paradox firewall hypothesis has garnered significant attention because it raises profound questions about the nature of black holes and the reconciliation of quantum mechanics and general relativity. If the firewall exists, it suggests that information is not preserved in the way quantum theory predicts. Instead, this information would be annihilated by the extreme radiation at the event horizon. Such a scenario would challenge our current understanding of physics and prompt a rethinking of how we approach the idea of spacetime and black holes. While the firewall hypothesis provides a possible solution to the information paradox, it has not been universally accepted. Many physicists are still grappling with its implications, as it introduces further complications in reconciling quantum mechanics and general relativity. Additionally, some theories suggest that the paradox could be resolved in other ways, without the need for a firewall. One of these alternative theories is the idea of the soft hair of black holes, which proposes that the information that falls into a black hole is encoded in subtle quantum states on the event horizon. Avoiding destruction, experimental evidence for or against the firewall hypothesis is extremely difficult to obtain, as black holes are far beyond our observational reach in terms of direct study. However, theoretical physicists continue to explore the consequences of the firewall idea by analyzing the behavior of black holes in both quantum and relativistic contexts. Models and simulations based on the firewall hypothesis are being developed to understand how it might manifest in practical terms. The information paradox firewall hypothesis ultimately reflects the ongoing tension between two pillars of modern physics, quantum mechanics and general relativity. While a final solution to the paradox remains elusive, the ongoing debate over the nature of black holes and the fate of information inside them has led to exciting new avenues of research. Whether or not firewalls truly exist, the exploration of this hypothesis pushes the boundaries of our understanding of the universe and may one day lead to a deeper, more unified theory of physics that merges quantum mechanics with general relativity. Superfluid vacuum theory, SVT, is a theoretical framework that aims to provide a deeper understanding of the fundamental nature of space and the vacuum. It proposes that the vacuum, often thought of as empty space, is actually a dynamic, quantum field, an entity that can exhibit superfluid-like properties under certain conditions. This theory suggests that the vacuum of space is not merely a void, but rather a complex, fluid-like medium that interacts with particles and fields in ways that challenge our conventional understanding of reality. The key idea behind SVT is that the vacuum is not empty but is instead filled with a superfluid, a state of matter that flows without friction. Superfluids are known for their unique properties, such as the ability to flow through tiny pores without resistance and to exhibit quantum effects at macroscopic scales. SVT extends this concept to the vacuum itself, suggesting that the vacuum is not a passive backdrop to the universe but a highly active medium that can influence the behavior of particles and fields. One of the most important implications of SVT is that it offers an explanation for the nature of gravitational forces. In traditional general relativity, gravity is understood as the curvature of spacetime caused by massive objects. However, SVT proposes that gravity arises from the interaction between matter and the superfluid vacuum. Instead of being a result of curved spacetime, gravity could be seen as a manifestation of the way matter interacts with the superfluid properties of the vacuum. This view could potentially lead to a new understanding of how gravity works at both large and small scales. The theory suggests that, just as superfluids exhibit unusual behavior at very low temperatures, the vacuum could exhibit quantum effects that influence the behavior of particles in ways we have yet to fully understand. These effects might include phenomena like vacuum polarization, where the vacuum fluctuates and temporarily creates pairs of particles and antiparticles that pop in and out of existence. According to SVT, these fluctuations could play a role in fundamental forces, including electromagnetism and gravity. Another key aspect of SVT is its potential to unify quantum mechanics and general relativity. These two pillars of modern physics have so far resisted being reconciled into a single, unified theory. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity describes the behavior of large-scale structures like planets, stars, and galaxies. SVT offers the possibility that both of these theories could emerge from a common underlying framework, where the superfluid vacuum serves as the unifying medium. This would represent a profound breakthrough in our quest for a theory of everything, a single framework that describes all physical phenomena in the universe. SVT also has implications for the nature of dark matter and dark energy, two of the most mysterious components of the universe. These phenomena have been observed through their gravitational effects on visible matter, but their true nature remains unknown. Some proponents of SVT suggest that dark matter and dark energy could be manifestations of the superfluid vacuum itself, with dark matter representing a condensation of the vacuum and dark energy arising from the vacuum's inherent energy. This could provide new insights into the nature of these elusive cosmic components and how they shape the evolution of the universe. critics of SVT argue that it is still a speculative theory and lacks the experimental evidence needed to verify its claims. While the concept of a superfluid vacuum is intriguing, much more research is needed to explore its validity and practical implications. However, SVT has sparked the imagination of physicists and cosmologists, leading to a growing body of work that seeks to understand the nature of the vacuum and how it might influence the fabric of the universe. In terms of its potential to change our understanding of space, time, and reality, superfluid vacuum theory offers a radical new perspective. It challenges the classical notion of the vacuum as empty space, proposing instead that the vacuum is a dynamic and active entity that plays a fundamental role in the behavior of the universe. This could have profound implications for fields ranging from quantum field theory to cosmology, as well as for our understanding of the origins and fate of the universe itself. Causal Set Theory. Causal set theory is a fascinating approach to understanding the nature of spacetime that challenges traditional views of the universe's structure. Unlike the conventional models of spacetime, which treat it as a continuous fabric, CST proposes that spacetime is fundamentally discrete, made up of a set of events that are connected by causal relationships. These events form a network, much like a graph, where the structure and connections between events determine the overall structure of spacetime. The core idea of causal set theory is that the universe does not operate on a smooth, continuous surface but instead on a discrete structure. In this theory, the universe's space and time are built from a fundamental set of discrete elements, called events, which are linked together by causal relationships. Each event represents an interaction or occurrence within spacetime, and the causal relationships between these events govern the geometry of the universe. Essentially, CST suggests that spacetime itself is composed of a collection of discrete, causally related points, much like a finely grained mesh or lattice. In CST, the relationships between events are not arbitrary but are governed by a strict causal order. An event in spacetime can only affect another event if the first happens before the second, creating a causal link between them. This causal ordering determines the structure of spacetime, and all physical processes in the universe are seen as the unfolding of these causal relationships. This is in stark contrast to the smooth, continuous nature of spacetime described in Einstein's general relativity, where spacetime is often treated as a continuous fabric that can be curved by mass and energy. One of the key ideas behind causal set theory is the notion that spacetime itself may be fundamentally quantized. This means that, at the smallest scales, the structure of spacetime might not be continuous but instead composed of discrete building blocks, just as matter is composed of atoms. In this view, the fabric of spacetime could be grainy at the Planck scale, which is around 10⁻35 meters, much smaller than anything we can currently observe. This quantization of spacetime could help resolve some of the unresolved issues in modern physics, particularly in the quest to merge quantum mechanics and general relativity. The discrete nature of CST offers a potential solution to several long-standing problems in physics. For instance, CST could provide a framework for understanding the quantum aspects of gravity. Quantum gravity is a field that seeks to describe the force of gravity in terms of quantum mechanics, but so far, no theory has been able to fully reconcile the two. CST offers a novel approach by suggesting that gravity might emerge from the interactions of discrete events in the causal set, rather than being a continuous curvature of spacetime. This could open the door to a deeper understanding of how gravity behaves at quantum scales. Another advantage of causal set theory is its potential to address the problem of the infinite density that arises in black holes and the Big Bang. According to general relativity, both black holes and the early universe involve regions where the curvature of spacetime becomes infinite. These infinities are problematic because they suggest that our current physical theories break down in these extreme environments. CST, by quantizing spacetime, offers a way to avoid these infinities, providing a more well-behaved description of black holes and the early universe. Causal set theory also has implications for the nature of time. In this framework, time is not a smooth, continuous flow but rather a sequence of events linked by causal relationships. The idea is that time, like space, is quantized, with each tick of time corresponding to the occurrence of an event. This approach to time challenges the traditional view that time flows uniformly and smoothly and suggests that the flow of time might be more akin to the unfolding of a sequence of discrete, causally connected events. One interesting aspect of CST is that it offers a novel interpretation of the nature of entropy. Entropy, a concept central to thermodynamics and statistical mechanics, is often described as a measure of disorder or the number of possible configurations of a system. In the context of causal set theory, entropy could be related to the growth of the causal set, the process by which events become causally linked over time. As the causal set grows, the number of possible configurations of events increases, leading to an increase in entropy. This interpretation could offer new insights into the nature of thermodynamics and the arrow of time. While causal set theory is still in its early stages, it has garnered significant interest from the scientific community due to its potential to resolve some of the most profound questions in physics. The idea that spacetime might be fundamentally discrete could have far-reaching implications for our understanding of the universe. It offers a fresh perspective on space, time, and gravity and could pave the way for a theory of quantum gravity that unifies the principles of quantum mechanics and general relativity.